AC motors are widely used to drive machinery for a wide variety of applications. To understand how these motors operate, knowledge of the basic theory of operation of AC motors is necessary. These are the objectives for this course. The principle of operation for all AC motors relies on the interaction of the stator magnetic field with rotor currents. The interaction between the magnetic field and the rotor current produces a usable torque. The torque provides rotation forces on the rotor, which can be coupled to desired loads throughout the facility. Before discussing what causes the rotor to start turning, we will discuss how a magnetic field is produced. There are two windings for each phase that are wound in the same direction. The magnetic field for each phase will depend on the current through that phase. Since the currents in the three windings are 120 degrees out of phase, the magnetic fields produced will also be 120 degrees out of phase. The three magnetic fields will combine to produce one field, which will act upon the rotor. This field is directed across the diameter of the stator and returns to the phase windings around the frame of the motor. This shows the rotating magnetic fields of the stator fields at 60-degree intervals, representing the three-phase current flow. For this diagram, when current flow in a phase is positive, the magnetic pole will develop a north pole for that phase, and when negative, just the opposite. At T1, phase C current is at its peak positive value, and the currents in phase A and B are halfway between 0 and the peak negative value. The combined magnetic field from all three phases is established vertically downward, with the maximum field strength developed across C phase. At point T2, the current sine waves have rotated through 60 electrical degrees. At this point, the current in phase A has increased to its peak negative value. The current in phase B has reversed direction and is at half of the peak positive value. Likewise, the current in phase C has decreased to half of the peak positive value. The resulting combined magnetic field is established downward to the left with the maximum field strength developed across A phase. And this process continues to where at point T7 the current is returned to the same polarity and values as that of point T1. So, by applying three-phase AC to three windings symmetrically spaced around a stator, a rotating magnetic field is generated. The speed at which the field rotates is referred to as synchronous speed. The field is rotating, but not the stator. Click to answer the question below. When alternating current is applied to the stator windings of an AC induction motor, a rotating magnetic field is developed. The rotating magnetic field cuts the bars of the rotor and induces a voltage in them due to generator action. The induced voltage will produce a current through the conductors of the rotor. The direction of the resulting current flow can be found using the left-hand rule for generators. To produce a torque or turning force on the rotor, there must be two conditions. A conductor carrying current must be present, and that the current carrying conductor must be in a magnetic field. The rotor of an AC induction motor cannot turn at the same speed as the rotating magnetic field because there would be no induced EMF in the rotor. With no induced EMF, there would be no rotor motion. The rotor must, therefore, rotate at some speed less than that of the synchronous speed of the magnetic field. This difference in speed between the rotor and stator fields is referred to as slip. The torque, or turning force on the rotor, of an AC induction motor is dependent upon the strength of the interacting rotor currents and stator fields and the relationship between them. During normal operation, torque is directly proportional to the rotor current. Rotor current increases in almost direct proportion to slip. The change in torque with respect to slip shows that as slip increases from 0 to approximately 10%, the torque increases linearly. As the load and slip are increased beyond full load torque, the torque will reach a maximum value at about 25% slip. The maximum value of torque is called the breakdown torque of the motor. If load is increased beyond this point, the motor will stall and come to a rapid stop. Typical breakdown torque varies from 200 to 300% of full load torque. Starting torque is the value of torque at 100% slip and is normally 150 to 200% of full load torque. As the rotor accelerates, torque will increase to breakdown torque and then decrease to the value required to carry the load on the motor at a constant speed, usually between 0 to 5%. Starting current in an AC motor is greater than the normal operating current that is drawn by the motor. The reasons for increased starting current. Starting current is typically 5 to 7 times the amount of the normal full load current. The motor full load current is the amount of current that a motor will draw from the power source when the motor is being used at its full capacity. This full load current is always shown on the nameplate of the motor. The starting current can be seen when a large motor with an ammeter is started. In many cases, the ammeter needle will peg high and then drop down to the normal operating current. It is normal and expected to see large starting currents. Once an AC motor is started, the operating or running current will be directly proportional to the amount of load placed on the motor. A common example is a motor turning a pump. As the flow through the pump increases when a valve is opened, the load on the motor will increase, causing motor current to increase. When the valve is closed, causing less flow through the pump, motor load and motor current decreases. Abnormally high operating currents are usually caused by mechanical binding of the motor or the associated component being driven by the motor. These high operating currents result in excessive heat within the motor, causing damage to the motor.